think we should start now. It's 9 o'clock.
Yes, ma'am, we can start now.
Okay. Good morning, everyone. Today's speaker is Dr. Manojendu Chowdhury. He's going to talk on exposure to X-ray binary data analysis. His chief interest is in academic sector. His research interest ranges from mainstream astronomy and astrophysics to mathematics education research. His teaching experience ranges from high school level to PG level, which is in subjects ranging from physics and applied mathematics to computation and management. He has been a team leader of Indian team to the International Olympiad in Astronomy and Astrophysics, as well as International Astronomy Olympiads multiple times. He has basically done his graduation from Delhi University, his post-graduation from IIT Delhi, and then he did his PhD from TIFR. His scientific research field is actually, first of all, he has an experience of this research for more than 20 years. And his research field is in high energy and astronomy, and that is in X-ray binaries, which is his topic for today's lecture. Presently, he is working for past more than 3 years. He is working with St. Xavier's College in Mumbai as a postgraduate teacher in physics department, where the MSc course is has specialization in astronomy. But before this, he has already got a lot of experience at working in different places with different institutes. Few of them are Ayuka, UMDI, CEBS, that is, is one of the courses at having situated, the location is Bombay University Kalina campus, HBCSC, BARC, and also he was associated with NCRA, National Center for Radio Astronomy, TIFR, Pune. So today we have a speaker who has a very good experience of doing research in the field which he is going to talk about to us today. So I hand over the mic to Dr. Manojendu. You can now start with your lecture. Thank you.
Thank you, ma'am. Thank you for this introduction. I think I'll stop my camera video for the sake of, data transfer. Okay, and I'll start.
1 minute, sir. One more thing. Would you like to
Yes,
take questions in between or at the end?
I think at the end. I'll take
Okay,
the questions
no
at the
problem.
end.
So
Yes.
we'll keep the track of
Yes.
questions and we'll put them to you at the end. So
Yes.
for all those who are here attending the lecture, please put your questions on chat box. Thank you. Go ahead, sir.
Okay, sir. Okay. Is that what I will do is that when I go to the web browser or something, then I'll stop sharing and start sharing that other window or something like that. Okay?
Okay, sir.
Okay. So now, let's start. So when I started off, when I agreed for this lecture on 1st of January, 9 a.m., I actually didn't comprehend that, 1st January morning is actually a very low energy period for people. And I'm going to talk about high energy astronomy. So let's see how I can infuse myself and everyone with high energy in this low energy period after the high energy period on the 31st of December. Okay. Now, before I get on with high energy astronomy, I like to tell that I will be talking about many things. Maybe I'll just rush through the slides and you can stop me if you want. But I'll be talking about many things which I feel is essential in addition to the processes that one takes, that are there for data analysis. There are many things a person should be aware of before starting or while doing the data analysis process, while undergoing the process. And, it is not possible to install the software that is used in kind of a thing, a trailer kind of a thing for the whole process that happens in the case of X-ray astronomy. Okay, and X-ray binaries in particular. So let's see how much I can cover during this time and how much I can move around, go to the exact software process and show you how things are done. And more importantly, not how things are done, but how things appear when you do them. That is more important, I feel. A person can do things by themselves when they want to get things done. But you need to know whether I'm doing it right or not. So that is what I'm going to emphasize on. That is what I'll talk about today mainly. So beginning with astronomy, I like to pose a question. And since there are too many people out here, you can, of course, you're always welcome to give your answers in the, type the answers and everything. But I may not have the time to go through all the answers, but I always pose a question and maybe pause for a few seconds so that you get to think about the answer and then I'd provide the answer. So now the first question that I'd pose is, what is the difference between astronomy and space science? Space science and space technology and astronomy. Because here lies the fundamental aspect of astronomy. Okay. Now, I'm just looking if there's any way I can look at the, the chat messages right now. But anyway, I'll see later. So, understand, astronomy is basically nothing but measurement of light. Everything that we know about the universe, which is directly from the measurement of light, that is astronomy. Okay, that is your electromagnetic radiation, your photons. Of course, nowadays you will be hearing terms like multi-messenger astronomy, where we talk about the gravitational radiation, which is a shear in the space-time fabric. And we also talk about neutrinos and astroparticle physics. So basically, where you're talking about particles other than photons. So then we are talking about multi-messenger astronomy. But when we are not using the word multi-messenger, then please understand, astronomy is nothing but measurement of light. The measuring detector used to be the human eye for so many thousands of years. And then in the last 100 years, we have developed the knowledge that all these cosmic sources, they emit through the whole electromagnetic spectrum, which our eyes can't see. So we observe them from radio to very high energy gamma rays. And hence, we need detectors that measure the radio to up till very high energy gamma rays. So fundamentally, astronomy is nothing but measurement of light. And when we are talking about measurement of light, we can measure light or photons as a function of three fundamental quantities which has been done. The fourth one is just in the nascent stage right now. The first quantity is your location or position. We are measuring light as a function of the position or the location. And that gives you an image. And the technique is known as imaging. Okay, the whole process that you undergo when you are measuring light as a function of its position is known as imaging. Then we measure light as a function of time. And when we are looking at the photons measured as a function of time, then the technical term that is used is the light curve. So what you see out here is technically called a light curve. Okay, basically how your flux is changing as a function of time. And the third and very, very important, perhaps from an physicist point of view, an astrophysicist point of view, the most important is the measurement of light as a function of its energy. And using energy, using Planck's law, you can convert energy into the frequency or the wavelength. And also, very, very importantly, you can measure that energy in different units. We will see that when we go from the radio to the X-rays and gamma rays, the energy changes or its units, okay, the units in which we measure. The fourth quantity, which is still in the very nascent stage, is that you are measuring light as a function of its polarization. And the main physical aspect of this is that you are measuring light as a function of polarization gives you an information of the magnetic field. Okay. Now, when we are looking at light as a function of position, so this is an image. You can see on the left, you see an Chandra Observatory's X-ray image. And on the right, you are seeing the image from the EHT. Okay. So the image on the left is actually an X-ray image. Please understand that these two images are X-ray and radio images, whereas what you see is a color, ranging from yellow to orange. These are all false colors. The color gives you the flux at a particular range of energy in which this image is taken. So please understand, this is a very, very fundamental thing which many people get confused, is that, mostly all the images that you see in the scientific documentation are false colored images, unless we are looking at an image that gives you the spectral information. Okay, so the image on the right is actually a radio image. Okay, it's not an image in the orange yellow range of the optical regime. And also the most important thing is look at the region where we are looking at this radio image. Okay, so we are taking this small region of the Chandra image, and actually what it appears as the dark spot, 1 pixel dark spot at the center of the Chandra image is actually, it is a peak of the image. Okay, it is just 1 pixel, and in X-rays we do not have the angular resolution to measure the size or get an extended view of that region. So when you are doing imaging, the most important aspect that one should understand is that what is the angular size that we can go down to measure the extended image. Otherwise, the image will appear like a single dot, a point source. Now here, Chandra is our X-ray observatory that has the best angular resolution. And you can see that we cannot see the center of this active galactic nuclei M87. Okay, so, and that is why when I will talk about X-ray binaries, we do not really talk about the imaging techniques, simply because we do not have the angular resolution in the X-rays to look at the extended view of this source. Whereas when it comes to radio, because of its long wavelength nature, we can actually measure the image at much, much better angular resolution. But you can see that there are extragalactic sources seen in other galaxies. So here we have something called M82. I'll not get into these source names, M87, M82. These are missile catalogs sources. So basically these all these M sources, messier sources, are extended sources in the optical regime. Okay, so this is a galaxy, and in this galaxy, using Chandra, we can actually see independent sources which are very, very bright in these galaxies. Okay, now, so in M82, we can see the sources X1 and X2. In fact, if you go to a better resolved image, you will be able to see other sources. So there are about 5 X-ray independent point sources resolved inside the galaxy of M82. Now, these sources are also considered, the MX1 and X2 and other sources, these are also considered to be binary stars, okay? Compact X-ray binaries, where the compact star is an, a black hole or a neutron star, okay? But it is very, very difficult to get some meaningful data to look at the light curve or the spectrum from these sources. They are too faint independently. It is a whole galaxy, the X-ray from the whole galaxy that you can see. Now, quickly going through, I will ask the question, what is an image? How do you create an image? Okay, so I don't think I'm able to see any, any output, anything that is, any text messages out here. But I want to pose the question, okay? So what is
Sir, if you
exactly?
can, sir,
Yes, yes, sir.
if you can click on the share window there at the top, you may get a bar.
Okay.
At the top bar, you can click on the chat, you'll be able to see chat.
Yeah, it's just that it is not showing me any chat option. Let me just check.
So on the black bar, it will be shown.
Yeah, in the black bar, I can't see any chat option.
Check under more.
More, okay. Okay, yeah, I can see the chat option out here. Okay, fine. Okay, I'm sorry, I was unable to look at the, the messages that people have. So a lot of people have responded about the, space difference between space and astronomy. Okay, I'm sorry, I missed them. Okay, so now, okay, somebody saying visual representation, somebody saying image collection of photons in the form of pixels. Okay, very good. But what I want I'm looking for an answer which is more specific technically. Okay, for example, look at the image that I'm sharing in my presentation. It's a very curved nature's reflection happening. An image is being created. Okay, but is this a very, very accurate representation of the reality? I don't think we can claim that. Okay. So if you ask me, all the definitions, all the things which are coming on my chat box, all these messages are actually very technical. I want to say something. Can you give a definition of an image to a high school student? Very, very simple, intuitive explanation of what an image is. Okay, people are giving and all of the answers that I'm getting in the chat box, they're actually correct. None of them are incorrect. You see, all of them are correct answers, but they're not simple enough. So I will say that an image is just, you see, I have an image here and an object here, right? So now can you tell me from here, give a very, very simple explanation of an image? Of course, it requires light. You are collecting light, right? But what does it happen? Suppose I'm looking at a tree in front of me or the window in front of me, and I have a paper facing the tree or the window. Okay, you can have, you have the object out here. I hope you can see my mouse cursor on the screen. You have the object out here, and you put a paper out here, or a photographic film or a CCD or something, and then you do not get anything. But the moment you put something like a reflector or some imaging thing, you get the image out here. Okay, it can be a reflection, it can be a diffraction, it can be neither. Okay, all of you are giving nice answers, but the answer that I am actually looking for is that when I have an object and I have a screen in front, then please understand that on the screen, the photons are reaching from all the points in the object. Okay? So any region here, the photon is reaching from this end all over. So all over the screen, I'm getting photons from all over this object, and they're getting all jumbled up. Whereas when I'm creating an image, then any one point in the image is actually getting photon from only one corresponding point in the object. Okay? One point in the object corresponds to one point in the image. Another point in the object corresponds to another point in the image. That's it. And this, in mathematical language, we'll call it a one-to-one mapping. So when you have a screen or a photographic plate or a CCD or your eyes, okay, and the light that is falling on these detectors from the screen to the photographic plate to your eyes, then the light falling at any given point in the detector is originating from only one point in the object. That is when you get the image. Okay, so an image is nothing but the best example of the mathematical operation of a function, or one-to-one correspondence. So even when you're looking at this particular image that you can see here, you are getting some reflection light, but this is a very, very distorted image. But every point in the image is all the photons which are reaching that particular point in the image are originating at one particular point in the object. Okay, so please understand that an image is nothing but a one-to-one mapping. It's a function. Okay, it's the best example of a function that we see. Okay, then all our imaging techniques, whether it is reflection, refraction, or other techniques, there are other techniques also other than reflection and refraction, they all attain this one-to-one mapping. Okay, so then what happens is that when we are talking about the imaging techniques, or if you go to the pinhole camera, then also if you have a small hole, every point in the image, the origin is only one point in the object. Whereas if you increase the size, then one point in the image can have objects, the photon can form multiple points in the object, and hence the image starts getting blurred. Okay, similar. Now I'll not get into too much of detail of imaging, but I just want to talk about the imaging of X-rays. Now, in X-rays, what is the difference between the main difference between X-ray and optical light? Tell me. I'll wait in the chat box. Main difference between optical light, optical photon, and an X-ray photon. Okay, energy wavelength, excellent. And what does that lead to? what does the energy lead to? Something more. When it interacts with the medium, understand your detector is a medium. Okay? When light falls on a thin sheet of paper, optical light falls on a thin sheet of paper, and an X-ray photon falls on a thin sheet of paper, what will happen? Okay, I can see many nice phenomena being mentioned, like ionization, photoelectric effect. Of course, these things are going to happen. But a more simpler thing, more simpler answer is that an X-ray photon will perhaps interact and pass through and get scattered. Okay, it will not be captured by a thin medium. And hence, when we are talking about mirrors, and we take a normal glass mirror or a metallic mirror, which we use for the reflection of the optical light, an X-ray will actually penetrate through. Okay, and hence it is not a very easy exercise to get X-rays reflected on surfaces. Okay, but you can do that when you are using a glancing angle reflection. And I'm sure you would have experienced sometimes, when you throw pebbles on water, they just sink. But if you throw pebble on a water at a glancing incidence, right? So basically, the pebble flies nearly parallel to the surface of the water, then it can bounce off. Okay, simply because of the two components of the momentum. Okay, one is the parallel component of the momentum and the perpendicular component of momentum. When you drop a pebble directly, normally onto the water surface, the perpendicular component of momentum is much larger, and that actually causes it to sink. Whereas when you throwing it parallel, then it is a parallel component is larger, and the perpendicular component which gets reflected is much less, and hence it can bounce off. Similarly, one can use mirrors to reflect the X-ray light at glancing angles, okay? And then you can have many different types of geometry of these mirrors to get the image out here. So again, you can see that we are actually creating a 1:1 correspondence, right? Now, okay, I think I should increase my speed, okay, and get on with more important, more complicated stuff. But yeah, let me get on with this geometries of the different mirrors. You can have a hyperboloid surface, you can have paraboloid surface, you can also have ellipsoid surfaces. Okay, so basically what these surfaces are, these are all conics which ensure that you have all the light focusing at one point, which is the focus. Okay, and the purpose of using all these all these conic geometries is that it removes the spherical aberration. Okay. Now, of course, there are Walter types, different kinds of Walter types of geometries are used, and depending on the nature of what you want to do, what kind of a detector you are trying to develop, you can have different kinds of geometries and you work out. Okay. But what is very important is that when you look at all these geometries, you see it is not just one mirror that you are looking at. You are looking at the design is such that you have multiple mirrors so that the effective collecting area is increased. Hence, you should be able to collect more and more photons. That will improve the brightness of the image. The number of photons that you're collecting, then that improves the flux that you're getting. Flux is nothing but energy that per unit time, per unit area that you are measuring, area of the detector. So by increasing the number of, changing the geometry and increasing the number of mirrors, you are effectively increasing the surface area of your detector. Okay? So once you have these kinds of detectors, Then you build the whole detector out here, and I'm sure you have heard of astrosats during your, or you hear of them more. Now, what I wanted to show out here is that this is an instrument in astrosat, which is your SXT, soft X-ray telescope. Okay, so this is a long tube of mirror, okay, which uses this Volter type reflections, glancing angle reflection. And what it does is that you have so many cylinders or mirrors, okay? And the idea of having so many cylinders is just that increase the surface area. How many photons you are able to capture into your focal point, okay? And quickly, we should also understand that when it comes to X-rays and gamma rays, like you do for optical CCDs, you actually record each and every photon that is reaching your detector. And these are recorded as events, that your detector is standing there waiting, and the moment a photon comes, it registers that an event has occurred. Okay? And these data are known as event mode data. Okay, we'll be using this term event mode data again subsequently a lot. So what happens out here, of course, I'll not get into too much of detail of the X-rays CCD of the CCD operation, but you should have an idea that you have something called pixels. Okay, each pixel is the a collecting area, the minimum collecting area of your detector out here. Okay, and of course, you have gas-based detectors and you have solid-state detectors. What happens is that the photon interacts with the material, whether it is a gas or a solid-state detector, and creates electron current. Okay, in case of gas, it uses the photoelectric effect and knocks off electrons from the atom. In case of your semiconductor detectors, it creates electron-hole pair from the depletion region. And what it measures is actually the electron current. Okay, and your electron current then converts the amount of current that you measure is then calibrated to the number of photons that has reached. Okay, what the photon of the energy of the photon that has hit the particular, that has created the particular event. Okay, and of course, quickly going through out here, when you are detecting an X-ray, your detectors can be multiple types. You can have a scintillator detector where the X-ray interacts with the scintillating material and gives out optical light, which is registered with the CCD. And historically, scintillator detector has been used in X-ray astronomy. But one disadvantage of these scintillating detectors is that, when it comes to the lab source of X-rays, you have a complete control over the energy of the source photon. And then the source photon interacts with the material, your medium. And here, the optical light that is produced is actually a statistical function. Okay, so there is an error bar introduced. Even if I have a monochromatic source of X-ray, there will be a distribution of energies in the optical light that is created out here. Number of photons that are created and also the energy of the photons and all. It is always a statistical distribution. Okay, so even if I have a monochromatic source of X-ray, when it comes to these scintillator detectors where we are doing an indirect conversion of the X-ray into the measurement of the flux, then there are errors introduced. To minimize the error, what is done nowadays is that you have an X-ray photoconductor, okay, and X-ray CCD. Okay, so what happens out here, you have an X-ray photoconductor which measures the X-ray and creates the current out here. Okay, I think I'll just unmuted myself. Okay. So now the advantage here is that the error propagation from a single photon of X-ray that is hitting the detector and the amount of current that you're getting is much less. But the difficulty is that creating an X-ray photoconductor or an X-ray detector is much, much more complicated. Okay. So we will not go into the the details of this kind of images, this kind of techniques which are there, but you should be aware that when you are analyzing the data, you are actually analyzing a statistical representation of the original photon. Okay, and that involves your whole detector response. Okay, if I have a monoenergetic photon coming, one photon, one energy, how does the statistics of the output change? You know, the output has an error bar. Okay, I'm sorry, I had a minor disturbance at my end. Sorry. Okay, let me continue. Okay, so I'll not go into the detail of this X-ray detection process, but yeah, you should understand basically you convert the photon's energy into an electrical current. That's the crux of it. Okay, now please understand that your reflection and refraction are not the only way you can create an image. Why? Because imaging is all about 1:1 mapping. Okay, if there are other ways of 1:1 mapping, then they can also be used for creating the image. So what you do out here, suppose look at this image. There's one red star out here or red object. Okay, you create something known as the coded mask. Coded mask is an asymmetric arrangement of opaque and transparent regions in a flat surface. Okay, it's like a mask, but what happens like in a mask that you wear, you have some holes for your eyes and nose and mouth. Here you have some asymmetric distribution of holes through which the photons can pass, and then you have locations where it is opaque. Okay, so what happens, each point creates a particular pattern of light and shadow in your imaging plane. Okay, so what you get out here is actually the convolution of your source with the detector response. Okay, so this is your detector response. You have to convolve the detector response function with the source function, and what you get out here is the resultant of the convolution. And then for each source, you have to deconvolve. Okay, each point in the sky will give rise to a particular pattern. So the red point will give rise to this pattern, the blue point will give rise to this pattern, and the difficulty arises that there is a region here which is actually the result of two convolutions. Okay, so basically now you have to, here these are point sources, so you can represent these point sources as Dirac delta functions. Okay, but if I have an extended object out here, then I cannot represent it as a Dirac delta function. I have to get the mathematical description of this object and convolve it with the detector's response. In this particular case, it is the pattern that I'm looking at here, and I'll get a composite pattern out here that you can see. Okay, so this is known as a coded mask, and this also creates an image. To get the image of the sky, you have to get this pattern that you see in your detector and do the process of deconvolution with this particular function, which is a detector response. And what you will get back is the sky map. Okay, and this is extensively used in case of X-ray astronomy, simply because we are looking at photons which are very difficult to reflect. Okay, so when you are creating an observatory, okay, all these X-ray observatories are basically satellite observatories because X-rays do not penetrate the Earth atmosphere. Okay, and hence you have to decide first what kind of observatory are you going to use and what kind of detectors are you going to use. Are you going to use the mirrors for detection, or are you going to use a coded mask? Okay, so in case of astrosat, certain detectors have certain ways of measuring the data. Okay, so this is just another example of having a coded mask. And if I have two beams, how does the shadow pattern of the two beams occur? And then you have certain regions which is the combination of both the shadow patterns. And obviously you can see that this coded mask makes the task mathematically more difficult, and hence there is more error introduced in the system, because ultimately all your photon statistics is dependent on the word statistics. Okay, and that is why you will prefer to have a mirror type reflecting reflecting mirrors out there, X-ray reflectors out here. But building an X-ray mirror is a very, very difficult proposition. So you decide on what kind of technique you have, what kind of technological support you have, and what kind of error you are ready to, tolerate. Okay. So another way of having a detector which is not an imaging detector. Okay, so now we are moving away from an imaging detector to other detectors, where you only measure the light curve and the spectrum. So a proportional counter is a very, very good example of a non-imaging detector. Now the question that you should ask is, if you are having a non-imaging detector, okay, then how do we know that the source is coming from a particular point? Okay, and multiple sources are not confounding your observation. Okay, I have two questions in my chat box. I just joined. Why is it asymmetric? You see, this is a very, very good and fundamental question. I was hoping that somebody will ask, and I mentioned the word asymmetric. I mentioned it, intentionally. The thing is, let's go back to the geometry. If I have a symmetric distribution, then look at the blue source and the red source and the blue source. If I have symmetric pattern, then, depending on the nature of the symmetry, the same position, the same kind of pattern will be repeated if I, change the positions. If it is asymmetric, then the pattern is completely dependent on one particular point. As I change the location of the points, the pattern will never be repeated. And that will reduce the confusion I have. Okay, so I hope the answer is there. Why is it asymmetric? Simply because we want to reduce the confusion. Okay. And okay, next question is that the data, is it affect the data? Of course, the moment you introduce something in your process, it will always affect the data and it will increase the error bar, and you have to mitigate the error bar in the best possible analysis procedure that you have. Everything that you do will have an error bar. Okay, every step that you take will increase the error of your observation. Please understand that. Okay, and we have to mitigate it in our analysis process. Okay, let's get on with. Now the question is, if I have a proportional counter out here and it is not creating the image, how do I ensure that it is coming from one particular point? The only way to do that, you have something called collimators. You see, these are long tubes, you can assume, okay? So these are long tubes where the photon, which is coming perpendicular, will fall on the detector. If it is coming at any other angle, it will be absorbed by these columns which are there, and they will not be detected. Okay? So collimator is another form, a more primitive form of a coded mask, you may ask, okay? Because here you're looking at the data only from the normal angle. Okay, only when the source is normal to you. Of course, there is a field of view, and that can result in error. So if there are multiple sources in a field of view, then your life is very difficult, and you talk about source confusion and other things. But you try to measure sources which are only object in your field of view. Okay. Now, when it comes to X-ray astronomy, we have reached the level that there are collimators which are very good. And given that X-ray sources are not that common, when you compare the number of X-ray binaries, which now numbers up to thousands, okay, then you see few thousand at most in our galaxy. Then you can see that, okay, they are much less in number compared to the stars that you see, the optical sources that you see, and hence the probability of source confusion is less. But let me repeat, there are situations where source confusions occur. Okay, so that is a difficulty you have to learn to live with. Okay, then we have something called, okay, so this is another spacecraft, RXTE. So you have detectors like this. Now, all of these detectors are non-imaging detectors, but we have got excellent scientific observations from these detectors, even though they are non-imaging detectors, and that is what we will go to. And the first thing that you measure is your light as a function of time, or you are measuring the light curve. Okay. Okay, somebody asked, why are you using a coded mask if it is not giving accurate data? You see, we are using coded mask simply because we cannot build a very good X-ray reflecting mirror all the time. But we want to create an image. We want to make observations. Okay? It is so you have to make do with whatever you have, right? So, okay. So now the thing is light as a function of time. I will quickly go through and give you an example that this particular object, Cygnus X3, is an extra binary. And you can see that this is how I measure the light as a function of time from this source. Okay. Then what happens is that this is a binary star, and the modulation that you see in this particular source is due to the binary modulation. Okay, when the compact object is going behind the companion star, the X-ray is getting obscured. Okay, and we see a dip in the light curve, and then again you see a rise in the light curve. And the question that you should ask is, what are these gaps? You can see gaps, right? Can anyone suggest what are these gaps? Why do you have these gaps out here? Come on, think. I'm waiting for a response in the chat box. Quick. Okay, somebody says absorption, energy fluctuation. You see, when I'm talking about a binary modulation, there is no energy fluctuation. Okay, it is not interference between sources. Okay, I'll give you a hint. This is a satellite observatory. X-ray observatories are satellite observatories. Okay, now understand. Okay, I'll give you another hint.
Towards the sun.
Yes, the thing is, your satellite is moving around the Earth with a period of about 1.5 hours. So there are situations when the Earth is blocking the source. There are situations when the sun is blocking the source. Okay, there are situations when the moon is blocking the source. Okay, so that is why you have to select the data, and somebody used the word GTI, which is very good, which is a technical term, which is known as a good time interval. And when you are analyzing the data, you have to create the good time interval and take the data from those intervals. Okay. Now, oh no, there's something has happened. I'll just stop this. Okay, stop the sharing and I'll come again. Okay, it is an issue with the office that I'm sharing. Okay, please bear with me for half a minute or something. Okay, I hope all of you can see the screen right now. So now what happens, understand, when we are looking at any such modulation, there is one very, very critical aspect of these modulations, and that is the time of the peak and the minima, the maxima and the minima, they are quite accurate. But the flux of the maximum and the minimum point, they can change. Okay, so I might have that here. You see here, I mean, in this, look at my mouse cursor. At the peak, you are seeing something around 2000 counts, whereas here you are coming down to something around 1700 counts, 1800 counts. Okay, this is a peak. And the minima here is something of the order of 800 counts. Here it is 900 counts. And here it is 700 counts. Okay, so please understand, when it comes to all these variabilities, which you see as a function of time, in most cases, the periodicity is accurate. Okay, that means the system is changing in more consistently in time, but the extent of the change, the amplitude of the change keeps on varying. So what you need to get is a template of your modulation. So how do you get the template? We'll discuss later. You basically take the average of many, many cycles, and hence you say that this is how the binary modulation in the source signal X3 is happening. Now, if you want to see how is my source behaving intrinsically, okay, it has a binary modulation, but the source also has its own change, right? So then you can see the figure at the right bottom, okay, which is the binary modulation corrected light curve. So here we have, so from this top light curve, we have subtracted this template. Okay, and we are seeing how does the flux change if you assume that the source is not a binary? The binary modulation is removed. Then how will it behave? Okay, and these actually gives rise to extremely important and interesting results. I don't think I'll have the time to discuss those results today, but this itself should give you an idea that whatever intrinsic change is happening in the source gets modulated. And ultimately, what in science, what we do, we take out the variables which we know and then explore the variables which we do not understand or do not know and explore what is happening inside. Okay, so if I want to understand what is the accretion physics happening out here, first thing, I have to remove the binary template and then look at the fluctuation here and then come to a conclusion, okay, this is what the source, this is what is happening inside. When it comes to the X-ray emission processes and all. Okay. So this is one of the first things that you do when you look at a periodicity in a X-ray binary. Okay. So now let's look at how do we physically explain this modulation. You have a system of two stars. This is a compact object, and this is an, mostly your X-ray binaries are evolved stars. Okay, they have filled your Roche lobe and they are throwing out matter to the companion. Okay, and when it falls on the compact object, which is a binary star, which is a compact star, what we mean by a compact star is that it is either a neutron star or a black hole. Okay, because they have the maximum compactness and which causes the maximum strain in the space-time curvature. Okay, they have the maximum curvature, you can say, in the space-time fabric. And when a particle falls in that fabric, the space-time curvature, it loses the gravitational energy. And that energy is emitted out as electromagnetic radiation. And because these are extremely compact objects, the amount of energy lost is very large. And hence, the photon that comes out is having huge amount of energy, which falls in X-rays. Okay. Of course, you normally have two classes of binaries, low mass X-ray binary and high mass X-ray binary. Okay. And the low mass, okay, so I'll answer the questions, okay? Now, the low mass and the high mass correspond to the mass of the companion. Please be very careful out here, okay? When I'm talking about the low mass and the high mass X-ray binary, I'm talking about the mass of the companion star. Okay? So, now somebody asked the question, why is the periodicity removed in binary modulation corrected light curve? I think I've answered the question. Okay, and how can you infer the accretion process from the modulated light curve? Okay, my dear friend, you have to go through the whole process of X-ray astronomy, okay, which honestly, I cannot cover decently in just this 2-hour lecture. Let's be honest, okay? 1 hour is already gone. Let's see how much I can cover. But you look at it, there are multiple, you look at the light curve, you look at the spectrum, okay, and then you come to the conclusions. Okay, how to go about it? I hope I'll be able to cover something today. Okay. Now, so you have an ordinary star and you have a compact object out here, and the mass is, in case of low mass X-ray binaries, in case of low mass X-ray binaries, it fills the Roche lobe and falls here, and by the conservation of angular momentum, it creates an accretion disk. And mind you, whenever we talk about a binary star system or a matter falling in, even when the young stellar object, when the star is forming, because of the conservation of angular momentum, an accretion disk gets created. Okay, so an accretion disk is a natural fallout of the spherical accretion process. But both can exist also simultaneously. For that, we have to go into the nitty-gritties of X-ray astronomy, which I don't think I'll have the time today. I'll just cover the very basics of what is done. But from the spectral analysis and also from the timing spectral analysis, combining the timing and the spectrum, you can get an understanding of the geometry of the disk that is happening out here. Okay, where how much is spherical accretion, the disk is truncated from inside, and you have a spherical accretion inside. So all these things are possible. Okay, now quickly going through this whole concept of your mass transfer, there are a few things you should understand. I think you understand what are Lagrangian points and all. So I'll just mention in the passing that when you have two objects stationary, then there's one Lagrangian point. When you have two objects moving around each other, then you have 5 Lagrangian points. L1, L2, and L3 are the balance points which lead to unstable equilibrium. And L4 and L5, these are very counterintuitive. These are Lagrangian points where you have a stable equilibrium. Okay, when we say unstable equilibrium, any matter here will either fall in here or fall in here. It will not remain confined here. You will find very little matter here. Okay, whereas in L4 and L5, if matter is here, it will remain in a stable configuration there. Okay, so if you want to know the details, then these are the mathematical formula that gives you the location of L1, L2, L3, L4, and L5, depending on the masses and the separation of the objects. Okay, but you should be able to visualize that this is what happens in a binary system. Okay, the whole system is rotating, and these points 1, 2, 3, 4, and 5 are points which are rotating, and matter, depending on which point it is, will go through the stable or unstable point, which you can see out here. Okay, and if you want to look at the 3-dimensional picture of the gravitational potential, then this is how it is. And these points L1, L2, and L3, they actually correspond to the saddle point in the potential energy curve. And hence, these are points of unstable equilibrium. Okay. Now, coming to the compact object. Okay, somebody had asked. Okay, there's more questions out. Let's check. Okay. Why is, if L1 is, an Aditya mission is in L1, okay, why is it targeting L1? Simply because it is easier to reach there. And you see, Aditya mission is a spacecraft, okay? It can correct for itself. And ultimately, it is a saddle point, okay? And understand the geometry from here. Let me just show you the geometry again. This point L1, you look at it. This point L1 is the closest to Earth. All of you appreciate this? Okay. And any point in L1, actually in all the points in L1, L2, L3, L4, L5, these points are tidally locked, right? So one part of the spacecraft is always looking at the sun. The other part of the spacecraft is always looking at the Earth. It's tidally locked. And hence, you will always get, there is no change in the location with respect to the sun or the Earth, right? And that is true for all the points. Okay, but L1 is the closest point to Earth. So when it comes to developing a mission, it is easiest to reach L1, right? So, of course, the satellite is orbiting around the point. Okay, Again, it is orbiting around the point simply because that point is a point of equilibrium. Although unstable equilibrium, it is a point of equilibrium. And understand, an object that is going around a point has angular momentum, and angular momentum is conserved. And hence, it can remain in a stationary state. Okay? Simply because of the conservation of angular momentum. If you just have a point sitting there, which is not, doesn't have any rotation, it will just keep on drifting. Okay? So you can, what happens is that you have the Aditya mission, which is moving, has an angular momentum about the inner Lagrangian point. And because of the conservation of angular momentum, it is stable around that point. And that point is a stable point in the Earth-Sun scenario. Okay? And because it is a stable point and it is closest to the Earth, that is why it is into L1. If you want to send to L2 or L3, L2 and L3 are more difficult. If you send to L2 and L3, I think immediately you'll see that in L2, it can only see the Earth. In L3, it can only see the Sun. Okay, it cannot see both the objects at the same time. Right? Whereas L4 and L5, these are points of stable equilibrium, but they are very far away. And hence, reaching those points will be extremely expensive. And we do not have the technology to take a rocket to that length yet. Okay, so that is why L1 is taken. Okay, so now let's get on with the type of objects that we see in extrabinaries. So one way of looking at it is that, you know, somebody had asked, how do you understand whether an object is a neutron star or what is the accretion process, whether it's a neutron star or a black hole or whatever? If you see pulsation in the source, then it has to be a pulsar, which is a neutron star. Okay? So one sure shot way of coming to a conclusion that whether a star is a neutron star or not is look for pulsation. If you see pulsation, you are convinced it's a neutron star. If you cannot see pulsation, then you have more exercise in life. Okay? So now this is how a pulsar behaves. All of you can see this animation, right? It is rotating and it has a very, very strong magnetic field, and matter at that energy is always charged, and the charged matter will always be tied to the magnetic field. It is spiraling along the magnetic field. And hence, when you have an accretion powered pulsar, that is the compact object is accreting the matter from the neighboring stars, okay, from the neighboring companion star. The matter will fall along the magnetic field. And where it falls, it will have a hot spot. You can see the hot spot region, okay? And normally the magnetic pole and the rotational pole are not aligned. If they are aligned, then you won't see any pulsation. But when they are not aligned, then you see that the magnetic field will rotate around the rotation axis, about the rotation axis. And hence, what you will see that there will be times when this particular pole will come in your field of view and you get a high flux. That is what a pulsar is all about, and you can see the data out here. By the way, you should look at this data. You should, take note of all this data. I can ask questions in the end, typically. What is the size? What is the magnetic field? Okay. What are the typical periodicities of a pulsar, of an accretion powered pulsar and all, okay? Whatever see the data on my screen, you should have, you should look at it very carefully and make a note of it. Fine. Now you can see that here you have a time-lapsed image of the vela pulsar known as a vela. And you have the pulse profile, okay, of this particular pulsar. So here you can see there in one rotation, you can see two poles. So you get two maximas, okay? If in a pulsar you see only one pole, then you will see only, then you can come to the conclusion that the rotation is happening such that only one particular pole is coming in your field of view. That constrains the geometry of the whole pulsar system and how it is aligned with your field of view, your line of sight. Okay. Now, how do you create this particular pulse profile? Or how do you make any measurements? Okay. So you have a light curve out here. And what do you do with it? I'll discuss a little bit in detail two techniques. One is the Fourier technique. Okay. Of course, you know what a Fourier transform is. I'll assume all of you are masters of Fourier transform. Then you should know that if I have a function in time, when I do the Fourier transform of that particular function, I get a function in 1 upon time. Okay. So I get to the frequency domain. Now here, when you see on the top left panel, you have a light curve, function of time, and the fluctuation that you have is completely random. And when it is completely random, basically it's white noise, then in the Fourier domain, again, you have a kind of a noise that you get as your Fourier transform. Okay. When you have a very, very stringent periodicity, a very, very strict periodicity that you see in the time out here. Okay. The difference between this middle panel, left middle panel, and the top, the top left panel, okay? Please understand the amplitude of these two light curves are nearly the same. Please appreciate this. This is extremely important. Okay, so now here, the amplitude of this variation and the amplitude of this variation, they are same. But the time interval from this variation and the time interval of this variation, they are of completely different nature. In the top left, the time of this amplitude variation is random. And here the time of the amplitude variation is very, very sharp time. It is, okay? But so what you are seeing out here, you have a random noise. And on top of that, you have a very, very strict periodic signal. When you do that, when you get that kind of alert curve and do the Fourier transform, we'll get a Fourier spectrum which has a very, very narrow peak. Okay. So that tells you that you have a very, very strong periodicity happening out here. Okay. Then when you have something called a quasi-periodicity, when you talk about quasi-periodicity, it means that your periodicity is not standard. It appears sometime. And at different regions, it can have slightly different periodicity. It is not a very, very strong period. The periodicity is not very well constrained in time, as well as, when it occurs. It might happen you have some periodicity in some finite time, and then it again becomes random. Okay. So then what you get in the Fourier domain will be a wide peak. Okay, and normally the shape of these peaks are Lorentzians in nature. Okay, and we talk about what is known as a quasi-periodic oscillation, QPOs, which are very common in X-ray binaries. Okay, so now this is a very, very strong technique. Okay, the Fourier transform. The next extremely strong technique is epoch folding. Okay, you have an epoch and you fold that epoch. Okay, so basically what is done out here, you look at this. You have this light curve from a particular source called Circinus X1, which is a very, very interesting source. Okay, now you have this kind of Fourier transform, you get kind of a periodicity of, some 16.6 days. Okay, what you do, you start from a point which you call as epoch 0. So this, and then take segments of the light curve corresponding to this period, which is, I'll say 16. And so this segment is this light curve. In this segment, okay, we have a completely different light curve. Okay, in this segment again, you see this light curve. In this segment, you see this light curve. In this segment is this. So you get to see in different segments, the individual variations can be very varied, very large of kind of variance. But when you add all of them together, okay, so what you are saying, you are kind of folding the light curve to that particular period. Okay, when you do that, so you take, this is just an example, take the first, 3 periods. Okay, so this is one epoch, this is the next epoch, okay, and this is the final epoch. Okay, so you're dividing the light curve into all these epochs, and then you are adding them. Okay, and what you get this as the resultant light curve, which is known as the folded light curve. Okay, and it is folded to 16.6 day period, and you get to see a kind of a, a folded light, a nature of the fold, or how the variation is happening. Now, if you take the same light curve and take a different period, say 10.5 day, then you won't see any such fluctuation. You see just random fluctuation. Okay, if you take the epoch corresponding to the actual fluctuation which is happening in the source, then you get to see a folded light curve which will have a definite maxima and a definite minimum. Here the minima is pretty broad, but the maxima is well defined. But if you fold it to any other period, then you won't see any particular maxima or minima. Okay, now understand, how do I measure the periodicity? I fold the light curve, this particular light curve, for many different periods, small, okay, and I get the different folded light curves. And then I fit a function which is a constant function. Okay, when I fit a constant function, then this particular, you just look at my mouse cursor, this particular folded light curve, if you fit to a constant function, will fit well, okay, with some random fluctuation. So the straight line fit will be good. Whereas if I try to fit this with a constant function, it will have a high chi-square deviation. And this, if I fit with a constant function, will have a low chi-square deviation. So I take this light curve and create huge number of epochs, large number of epochs, fold them to the epochs and fit it with a constant function and see which particular periodicity has the maximum chi-squared deviation. Okay? And if I'm looking at a pulsar, which has a very, very well-defined periodicity, then I'll have a very narrow period for which it will have a very strong periodicity. Okay? So this, the tool, you see, when you are analyzing the X-ray sources, the most important tools, the most important set of software that you use are known as F tools. Okay? So the F tool that you use is known as EF search, epoch folding search. Okay? And here you have created so many different epoch, so many different light curves and fit all the light curves with a constant function, and you find the folded light corresponding to the particular time period which has the maximum chi-squared deviation. Mind you, in data analysis, you always talk about chi-squared minimization, but when it comes to epoch folding and you're looking for a periodicity, you're actually looking at the maximum chi-square deviation. Okay? And that is your period, accepted period. Okay? And then this is the folded light curve corresponding to that particular periodicity. So what we are saying is that the source Centaurus X3, when we took the light curve and did an EF search through a range of periodicity, and we were very happy that for a period of 4.8091 seconds, I got a very high square deviation. So this source has a very, very strong periodicity at 4.8091 seconds. And this we infer as a pulsation period, rotation of the node. And then we fold the light curve to that period, and we get this kind of a profile. Mind you, this is, whenever you look at the folded light curve, you use eFold. The tool that you use is eFold, okay? And you normally always show two phases. So these are two full rotations. And here we are able to see only one peak in one rotation. Okay? The maxima corresponds to the binary phase, phase that we have out here is about 0.1, 0.15 between here, and the minima is about 0.8. Okay? Mind you, you can change the initial epoch, the initial starting point, and here you can actually shift this epoch. Okay? Okay, there are a few questions. Let me look at the questions. And analyze it multiple ways and look at the consistent result. Okay? Because three different data, by the way, data is plural and the singular is datum. So there is no word as datas. Okay? Please understand that. Okay? So when you're looking at the data, you take the same set of data and you try to analyze the same set of data in multiple ways and then see what result is the consistent result. Okay. And this whole light curve and divide it into segments. Each segment is one epoch. Okay. So when you sum them up and fit for the data, okay, sum them up for different frequencies, for different periodicities, and you fit a constant function. Then for the periodicity which has the maximum deviation, chi-square deviation with the when fit with the constant function, is the periodicity that you're looking for. Okay. So that shows that your source has a very, very strong periodicity. Okay. And this is the epoch folded light curve. Okay. Of the source Centaurus X3. Mind you, in the previous slide, we were talking about Circinus X1. Here it is Centaurus X3, different sources. Okay. Fine. Now, I think let me. Okay. And improve the feature of the data. Okay, if you're looking at a pulsation, improve the pulsation period. How do you look at the pulsation period? Okay, even if I do not have a, if I'm looking at a light curve, how would I know what the pulsation period is? So you need to have techniques for that. Okay, I am measuring, I don't know what the periodicity or the frequency is. So that is why you have these techniques. Okay. So now, quickly, you should know, I'll just go through the concept of quasar and microquasar. Quasar is an extra binary, a compact object, accreting matter. Sorry, a quasar is supermassive black hole, center of the galaxy, active galactic nuclei, accreting matter from the whole galaxy, basically the galactic neighborhood, and it throws out matter. Microquasar is, a compact object getting the matter from the environment. Now I'll take the look at the, let me look at few of the tools that we can use. Okay. So let me now share another different window. Okay, I hope all of you can see my browser window.
Yes, sir.
Okay, so first look at the light curve. Basically, these are the prompts that you get out here. Okay. One very important F tool, I said, the set of programs which are used for X-ray astronomy are known as F tools, the standard. Now understand, every observatory has its own data. So to get from the raw data to get to a light curve, every observatory will have its own set of programs, own set of F tools. Once you obtain the light curve, then you have a common set of F tools for analyzing the light curve. So once the light curve is obtained, it doesn't matter what the observatory is. But to obtain the light curve, we have to use the observatory specific tools to reduce the data. Okay. So now, one such tool, F tool, for looking at the light curve is known as L curve. Okay. So when you run the program L curve, it'll ask for inputs. You say one input file. You can input up till 8 files out here and give the light curve, which you have already installed, which you have already extracted. So the assumption is that you have the light curve with you. Okay. If you do not have the light curve with you, go to the observatory data and get the light curve. But that takes time. Okay. So I'm just telling you that, okay, the light curve for the Sen X3 is here. Once you give the light curve, then it will give you the source name from the, it will read this. These are all the data that the software reads from your header file. Okay. So start time, stop time, bin time. This is your, what is the time resolution? Understand, this is very important. Where we said that every particular photon that reaches the detector is recorded as an event, right? But you do not plot the light curve for every independent event. What you plot is in a given time interval, how many photons reached. Next set of time interval, how many photons reached. Next set of time intervals, how many photons reached. Okay. So that is the extent of the time interval is your bin time. Okay. So that is what you give out here. And you can change the bin time. You have the default bin time of the light curve. It is 0.125 seconds for this particular light curve. And here, if you look at it, you are providing a bin time that is 1 hour. Okay, that means you are not looking at 125 millisecond light curve. We are looking at a 1 hour light curve. So basically, you have huge set of observation, huge observation. If you look at 125 millisecond light curve, you won't be able to see much. It will be all random fluctuation appear with large error bars. When you increase the bin time, because of the propagation of Poisson error, the error decreases. Okay. And so then it says it has 92 new bins. That means it has 92 stretches of 3600 seconds. Okay. And then you plot them. So what you plot is basically a histogram. Okay. So starting from 0, you have so many in the first bit of 3600 seconds, you have something like 2000 counts per second. Then your count increases drastically. Okay. And here you see a fall and it increases and you see a fall. And after some time here, it comes to very low value. Then there is a gap out here. Okay. You do not see the observation out here. And here again, it comes out here. Now understand, this is a very, very long exposure. In the previous light curve, for Cygnus X3, you had short exposures and then gaps. Here, the gaps are very, very long. Simply, it shows that your particular satellite has a different orbit. And it can look at the particular source for a long stretch without any disturbance. Okay? And this is how your source is behaving. This is a light curve of this particular source. If you go to the next exercise, when we take this particular light curve, same light curve actually. Let me increase the font size. And now you run another tool called Power Spec. This tool gives you the Fourier transform. Okay. And when this happens, you input the light curve, and I'll not go into too much of details of these inputs. Okay. But what you will get in the end is the Fourier transform. And you can see that the Fourier transform has power at this particular frequency. It is a very, very large power in one particular frequency. And this frequency, okay, this, if you look at it, this is something of the order 0.21 or 0.22 hertz. And this is something of the order 0.42 or 0.44 hertz. So this is the harmonic of this particular frequency. So whenever looking at Fourier transform or the periodograms or something, then you look at the harmonics also. Okay. Then what you do, you know the frequency. So from there, you take the time period and you run EF search on the same light curve. Okay. And then you get a periodicity at that particular period. Okay. 4.8091. So understand, when it comes to periodicity, EF search gives you a better resolved periodicity than a Fourier transform. Okay, because in Fourier transform dealing with 1/t. Here you're dealing directly with t. Okay, so here you run the program EF search corresponding to the Fourier transform. the periodicity with the Fourier transform and also with a particular stretch you look for, and this is what you get. And then when you run E-fold, okay, you run E-fold out here, then you will get the folded light curve of this particular. Is this clear, everybody? This is how you actually take a pulsar data of an X-ray pulsar source and get the pulsation period. Okay, I have lots of questions out here. Let me just see if I have time to. Okay, now let's come to exercise 4. Okay, this is something I'll just show that if you have a periodicity that is changing. Okay. So mind you, here we are taking a different source. Okay, this is a different source, different light curve. Now the periodicity is not as stringent as the previous source. Then you see, when you look at the result of the EF search, epoch folding, this is the kind of periodicity that you get. And if you take this particular period and fold the light curve, okay, sorry, I mean this, when you see this, you change, okay, and okay, you change the parameters to get better stringent handle on this, then this is what you get. Okay, so whenever I have a change in periodicity for whatever reason, okay, then I get a different result. And when I'm looking at the effect of the orbital motion on the pulse period, so now what you are getting, mind you, is a result of two periodicities. Okay, and also when it comes to orbital motion, understand the location of the source is changing, right? So if the source is nearby and the rotation of the source is also visible to you, then what you get is this kind of a feature. It is now a wide pulsation. Okay. So this wide nature, okay. So now when you fold it as per the orbital modulation, this is the kind of orbital modulation, periodic change that you get in the pulse period. Okay. So your pulse period will now change. Okay. So what you need to do is you take for different stretches of time, take the light curve. Okay. So now what happens is that the different stretches of the light curve corresponds to different binary phase. Okay. And then do the EF search for each phase independently and measure what is the periodicity you're getting. And then measure the periodicity as a function of the binary period. Then you see that the periodicity keeps on changing. Okay, because now your pulsation period is superimposed on a rotation. You can imagine if you are sitting in a chair and rotating a torchlight and a person is observing the rotation period of the torchlight. Now imagine you are sitting on a merry-go-round and you're rotating the torchlight. What the stationary person sees is your rotation of the torchlight and the rotation of the merry-go-round. Okay, and hence the periodicity will be now modulated. Okay, so this is the effect of the binary modulation that you get. Okay, then and of course, what is very, very important to understand in that shift is the Doppler shift, because the time of arrival of the each pulse is now changing as per the rotation. Okay, then what happens is that, okay, this is your folded period, pulsation period, corresponding to the mean time that you have out here. Okay, and you get to see for different parts of the binary phase, you get to see slightly different, nature of your folded light curve. Okay, then we were talking about quasi-periodicity. Now, quasi-periodicity is a periodicity we believe is associated with the accretion disk. And when we observe a light curve which shows quasi-periodicity, this is how it looks like, that this is your Fourier transform. And on the Fourier transform, you have a wide peak. This whole nature is known as a noise. And superimposed on this noise, you have a periodicity but this periodicity is different from the pulsar periodicity. Here, the periodicity is wide in nature. Okay. So then what happens? Let me just finish this. When this periodicity happens for very high frequency, this is an amazing result from RXT. You have a frequency period that is about few hundred hertz. Imagine you are looking at a neutron star, okay, the accretion disk around it, and you're looking at a periodicity of the order of something around 700 hertz, 800 hertz out here. It is very near to 1 kilohertz. The highest frequency observed is 950 something hertz. Okay. So because they are near to your 1 kilohertz, these are known as kilohertz QPO. These are very, very difficult measurements because you need very precise electronics for such a well-resolved time light curve, which can show periodicity. Okay. And RXT PCA was one such instrument which had the best possible detection of this. In fact, the first possible detection of these QPOs, and it was followed by AstroSat LaxPC, where you have observed the kilohertz QPOs in the same sources. Okay. Now I will stop sharing this particular, okay, and quickly go to something known as the spectrum. Okay, I don't think I'll have enough time to cover everything in the spectrum. Okay, because we have and I didn't really expect, but all of you understand what is spectrum, right? Just share the screen with you now. Okay. All of you know that spectrum is you plot the energy as a function, or you plot the photons as a function of your energy. Now, most important thing, one particular source, depending on time, at a particular day, it can show this kind of a spectrum. On a different day, it can show this kind of a spectrum. So these are known as the spectral states of the source. And somebody had asked, how do you know what is the nature of the accretion physics and whether it's a black hole or a neutron star or whatever? You study these spectrum, you model them, and then you understand that, okay, this is the spectrum from this particular source, and this is the physics that is happening out here. Okay, I'm very sorry. My office creates these problems for me, actually.
Sir, shall we use 2 minutes to take a quick poll?
Okay, I'll just show this particular slide, couple of slides, and then we'll go for the poll.
Sure.
Okay, this is very, very important because I want to. This is extremely important. Even if you don't understand anything of spectra, you should understand this much. That's what I feel. Okay, so all of you can see this electromagnetic spectrum, see the slide, right? So understand, when we are looking at the electromagnetic spectrum, you are moving from the radio to the gamma rays. Now, you measure different regions of the spectrum in different units. When we are talking about the radio astronomy, the most natural unit you measure the spectrum is in wavelength or the frequency. So when you're moving from 3 megahertz to 30 gigahertz, okay, that region is known as your radio wavelength. And then what you have is the millimeter, sub-millimeter wavelength, okay, which corresponds to 30 gigahertz to few terahertz. Then you go to the infrared regime from few terahertz to few hundred terahertz. And then comes the good old optical regime. This is the regime in which our eyes are sensitive. It is for a very, very short regime. 3 into 10 raised to 14 to 10, about 10 raised to 15. It is actually of the order of 7 into 10 raised to 14. But, sometimes some people can go up till 10 raised to 15, okay? So, normally we take as 7 into 10 raised to 14, okay? Hertz. Then comes the ultraviolet regime, 10 raised to 15 hertz to 10 raised to 16 hertz, okay? And then you have X-rays, 10 raised to 16 to 10 raised to 19 hertz. And gamma rays greater than 10 raised to 19 hertz. Now, when it comes to the radio, we talk about megahertz. But when it comes to the X-rays and gamma rays, we treat light as particles. The detectors treat light as particles. As I said, each photon is recorded individually. Whereas when it comes to the radio dish antenna, it records the electromagnetic wave. And we talk about the wavelength. When it comes to the optical regime, mind you, optical regime is the bang center. Okay? And our detectors actually make use of both the wave and the particle nature. When it comes to the optics, designing the deflection, refraction, and everything, the lenses and mirrors, we take the wave nature of light. And when it comes to the detectors, whether the CCD or photographic film or something, we take the quantum nature of light. Okay, so the particle nature becomes more prominent. When it comes to the X-rays and gamma rays, okay, we talk about particle nature of light, and that corresponds, the most natural unit is electron volt. So you talk about X-rays from 0.1 kilo electron volt to about a mega electron volt. And gamma rays, normally you talk about greater than mega electron volt. But there's a big but out here. Okay, please pay attention. The main difference between an X-ray and gamma ray is not on the energy of the photon, but on the source of the photon. So when we are talking about the laboratory sources, we are talking about gamma rays when the photon is emitted from the nucleus. And we talk about X-rays when the photon is emitted from the electronic transitions. Okay. And there can be a big overlap when it comes to the energy ranges. When it comes to the cosmic sources, then we talk about gamma rays. And nowadays, also in our laboratory sources, when we can do a greater than 1 mega electron volt or even few 100 kilo electron volt, we talk about gamma rays. Okay, but there is an intervening region where it can be confusing whether it's X-ray or gamma ray, depending on the tradition or the convention. You call it X-ray or gamma. Okay, but the origin of X-ray and gamma ray is from the atomic nature of the source and the nuclear nature of the source. Okay, so please don't get confused. Now, if we are looking for a thermal distribution, okay, then your radio sources are corresponding to very, very small temperature, and hence your sources have to be non-thermal. Okay. When it comes to infrared and optical and ultraviolet, your cosmic sources can be thermal. When it comes to X-rays, this becomes very, very violent, and there is a thermal component and non-thermal components like inverse Compton scattering and synchrotron come into place. Whereas for radio, the thermal radiation is so small, it cannot give rise to these emissions. And you look at either the hydrogen line, 21 centimeter line, or you look at the what you call the synchrotron sources, basically the non-thermal sources. Okay. And when it comes to gamma rays, again, looking at temperature above 10⁻⁶ to 10⁻⁹ Kelvin, theoretically you can have a black body at that temperature, but in truth, matter doesn't exist at that temperature because it will be ionized. So you don't really talk about thermal sources at that temperature. Okay. So these are the typical boundaries we are talking about for the things about boundaries. Okay, so you can take a quiz now. I won't go beyond this because I'm already running short of time. Okay. Quickly. Hello?
Yes, sir. Okay, so we'll go for a
Yeah.
quick poll.
Yeah, very quick poll. Yeah, very quick poll.
The poll is announced. All participants can answer this. Answer in 2 minutes. I will end the poll in 10 seconds. ending the poll. Thank you, sir.
Did we go for question answers?
Yes, we can go for question answers. The questions I have shown the slides which are very important.
Right.
If you want, I
Uh,
can
there
re-show.
is
I
one-
can go back to the previous slides also.
uh,
So basically, I want people to practice this particular. So,
Right.
okay. Now
there is
looking
one
at the
question here which is not taken up because you were otherwise looking at the chat box and taking the questions. I think this
yes.
last one you haven't taken up. That is what is slew rate is asked us.
Yeah. Oh, yeah. I was just about to take that. Okay. So the thing is, I think one person is an extra astronomer. Okay. One person knows about extra astronomy. And that is, I think the same person will ask a slew rate question from the poll. I can see that one person knew everything before. I'm glad you knew. So the slew rate is the rate at which a detector moves from observing one source to another source. And the data that you observe in between, which is used for measuring the background, is the slew data. Okay, it is essential that you observe, have a handle on the background. So to model the background, you continue having the, you continue to take the data. So when you're moving from one particular source, you move your detector through the sky and go to other source. That rate at which it is moving is the slew rate. Okay, and the slew data is used for background estimation and all. It is very useful for the instrument team, basically.
Okay, participants, if you have any more questions, you can put them in the chat box.
Even they may unmute right now. I've just opened the mic.
Okay. So, if you have Nivedita, I suppose you have raised your hand. You can unmute yourself and ask the question.
Yeah, hello, sir. Good morning, sir.
Good morning.
Yeah, sir, that thing I have asked about the slew rate. Sir, when you take a data, when you consider a data for analyzing, which data is better, like after the slew rate or before the data which is taken before the slew rate or
No,
after the slew?
you don't take the slew data at all. Okay, you take the data when it is observing the source. Okay, the slew data is meant for the background team. Okay, if you do not know, if you are a newcomer, don't even bother about the slew data. Okay.
Oh, okay,
So,
sir.
okay. If you are a part of the instrument team, then talk to your particular team. Because every detector has its own way. It's a very extremely complicated process. Okay. And also the
Is it
nature
for
of the
calibration?
sky.
Yeah.
Yeah, you see, it is used for calibration also, but for calibration, normally we look at standard sources, not at slew data. Okay, so we look at crab, and for hard X-ray, you look at Cygnus X1, because during the steady state, Cygnus X1 also has a very steady spectrum. Okay, so then you do the calibration as per these data, and slew data is mainly taken for the background. When you're not looking at the source, what is the count that you're
Okay.
getting?
Okay, sir. Okay, sir.
Okay.
Thank you.
But it might happen that when you're moving from one source to another source, there are other sources available in the sky, weak sources or something, or maybe some bright source also. That can also affect your slew data. So you have to take into account all those things. So they are normally handled by the instrument team, not by a person who is just starting to analyze the data or something like that. Okay?
Okay, sir. Thank you, sir.
Else, please raise your hand if you have a question.
Well, there's a question about pulsation and water data. Basically, you look at the spectrum, you look at the timing, and then there's huge amount of things that you can measure actually. Analysis is a very, very involved process. Frankly speaking, I'm still learning. So your question is that, a huge amount of things can be learned. You have to, that requires a different lecture. I know it's not possible to cover everything in a 2-hour time period, right? You look at the accretion process basically and look at the accretion ejection mechanism. You try to measure the velocities and all, but these are the things that you don't always measure directly. You do a spectral modeling and you try to infer these quantities from the model, physical model that you statistically fit with the data.
Any
Okay.
more questions? Yes, Swayam.
Sir, what the Doppler effect has effect on the collecting data? For example, we are taking the data from a source and that object is receding or
You
moving away
see,
from his.
understand, you have a source and it is emitting your sine curve. Okay. You will get the trough and the crest of the sine curve at particular periods, particular time intervals, right? Now that source is moving to and fro. So now that sine curve origin is changing. Okay. So the time of arrival of the trough and the crest of the wave will change. Right?
Yes, sir.
So that is what is happening out here. You can have a to and fro motion, but instead of to and fro, this is an orbital motion. So it's an elliptical orbit. So what you can resolve your orbital motion into a perpendicular and a parallel component, right? If it is circular motion, then the parallel and the perpendicular have the same radius. If it is an elliptical, then you'll have two different components, A and B, the semi-major axis and the semi-minor axis of the ellipse, right? So now you're depending on the orientation of the ellipse, you will see an effective to and fro motion due to the binary modulation, right? So that effective to and fro motion will alter the time of arrival of the typical, the sine waves crest and trough, right? So that your time of arrival gets modulated. And hence the time period that you see between the successive waves will get changed, right? Your wavelength, effectively your wavelength is changing, right?
Thank you, sir.
Okay, we can take one or two quick questions if there are any. Anyone has any more questions? Sir, I don't think there are any more questions.
Okay.
Actually, I myself enjoyed this lecture a lot. I
Thank you,
always had a little bit concern about this astronomy as not a subject that I would understand. But now I'm feeling that I should come and attend your lectures in the college so that
Okay, man. You're most welcome.
because you explained it in very nice, simple way that I started understanding astronomy a bit. And now
Thank
I
you,
think I
ma'am.
should attend your lectures more. And I'm sure
Thank you.
everyone has enjoyed the lecture and their doubts also you clarified as and when possible, looking at the questions in between, and that was very nice. So thanks a lot for your lecture, sir.
Thank you, ma'am. Thank you. It means a lot coming from you.
Okay, thank you, sir.
Okay. Okay.
Mahesh, sir, should we?
Thank you, sir. Yes, all participants, we will start our next session at 11:30.
Okay, so I'll then